sync type of approach here. So let's talk about it. Right off now, let's talk about flowcharts. So flowcharts are your friends. So if somebody gives you some programming to do, here's a challenge, go ahead and do it. So we talked about this a little earlier today. So what do? Hey, here's a problem, solve it. You just sit down and start cranking out some Python code? Some of you probably do. However, it seems as though it would be better if you sort of thought your way through the problem first, right? And I think somebody mentioned, sit down and do some sketching. That's cool, that's fantastic. And if you're one of the rare and strange people who can just start to crank out pseudocode, well, great, that's fantastic. Most of us really like pictures. Pictures make it a little bit easier to wrap your head around what's going on, and sometimes you're able to uncover like things that you didn't realize, relationships between different conditions and stuff that might not show up. And that's exactly what a flowchart is designed to do. Okay? It simply shows the structure of decisions and tasks that are required to solve a problem. If you have to do a complex problem, it's a good idea to draw the flowchart. Once again, it's so you can basically visualize the problem. You don't have to draw a flowchart for the whole shoot match. You can just draw a flowchart for a portion of the problem. Okay? What do we have over here? Oh, this is like from our tax program, remember? Are you single? Yes or no. If you're not single, then you must be married. If you're single, then is your income less than $32,000? If it is, then you're just in the 10% bracket. If it's greater than $32,000, you got to pay some additional money, and you're going to take 25% of your salary. If it turns out that you're married, are you making less than 64 grand? If so, then it's just 10%. If you're making more than 64 grand, then they're going to take some of your money, and they're going to charge you 25% on everything over 64,000. I could talk to you about that, but go straight over your head. That's so incredibly boring, right? But if I give you a flowchart that looks like this, then all of a sudden it becomes a little bit easier to wrap your head around what's going on. You go, oh, okay, I got it. So there's like three main decisions there. Okay, and 4 possible outcomes. Okay, the basic idea behind a flowchart is actually pretty simple. You link tasks and then put output boxes in the sequence in which they should be executed. You can have all sorts of boxes in a flowchart. But the simple three are, number one, a square. It's just a simple task. Do this, okay? A little slanted, I don't know what that's called. What is it, a rhombus? Is that what it is? Okay. Slanted one is input-output. You ask user for first name, ask user for social security number, ask user for credit card number. And then, of course, our old friend, Mr. Diamond, is, of course, the condition, all right? So make a decision. You've got 2 different ways out of the diamond, depending on whether it's true or false. Use a diamond, and each branch can contain a sequence of tasks and even additional decisions. So it may be true, but then maybe I've got more decisions, and I can make a whole bunch of different things going on. All right. Multiple decisions. If there's multiple choices for a value, use a whole bunch of diamonds. Diamond number 1 is choice 1, true, false. Choice number 2 is true, false. And of course, choice number 3 is true, false. And in this one, you just end up doing something in the tail end. Right? So it's really, really easy on a flowchart to have multiple decisions. And a good thing because most programming situations require you to make a whole bunch of decisions. Spaghetti code. Spaghetti code is, although spaghetti is a delicious and tasty dinner, it's actually something you really don't want to do in your program. Okay? So let's talk about this. So unconstrained branching and merging. So if your code's going from here to here to here to here, that's considered to be spaghetti code. Basically, spaghetti code is hard for somebody to interpret. What the heck's going on? Okay? It's hard to read code. It's considered to be spaghetti code. It's a messy network of possible pathways to a program. And just imagine if you handed your program off to somebody for them to create a test case. And you look like here, here, and here. And it's going to be just crazy for them to create a test case, right? Simple rule for avoiding creating spaghetti code. Never point an arrow inside of another branch. Which is great to say, but it's hard to visualize. So let's take a look at this. So here we go. We've got a pretty simple situation here. We're writing a program that calculates shipping costs for packages. Okay, cool. So shipping costs are $5 to any location inside the United States. If you go to Alaska or Hawaii, it's going to cost you $10. And oh, by the way, if you ship it internationally, it's also going to cost you $10. Just can't be that hard to do, right? Okay, calculate shipping costs. Are you inside the United States? Yes. Are you inside the continental United States? Yes. Your shipping costs are $5. Okay. Are you inside the United States? No. Okay, shipping costs are going to be $10. All right, we're pretty much there. The one thing we're missing from this, of course, is the whole Alaska-Hawaii thing. And how much does that cost? $10. All right, so we got to stick it in here someplace. One way to do it, and the complete wrong way to do it, would be to say, okay, so if you're not in the continental U.S., then we'll just tap over here, because we already have shipping costs equal to $10. We already have the code to do this. Let's just tap in here and use the code, because it's already there, right? And you're right, that will work. Unfortunately, things get messy here, okay? And that's considered the spaghetti code. Why? How did you get here? 2 different ways to get here? That's crazy.
You can just say, just make the initial question inside continental US.
So if you move this one up here, okay, inside continental US, then you would have 1 half to there. That's true, and you're exactly correct. However, in this statement of the problem, they broke it up into 2 points, right? So they said international. So admittedly, today, they're both $10. The thought is perhaps in the future, international goes up to 12 and Alaska to 1. So once again, you're exactly correct. But they broke it up in the statement of the problem into 2, perhaps with Alaska to 3.
And if the one goes up, you're going to have to decode it separately anyway. So that's exactly right.
So how do we solve this spaghetti problem? It's actually pretty simple. What we basically do is we duplicate the code. And I know I told you don't duplicate code, but this is one case where you actually do want to do it. Okay? So inside the US, true. Inside the continental US, no. I'm in Alaska, Hawaii, and then go down to the cost of $10. Notice it is the same as there, but that's also cool because if international shipping rates go up to $12, then you make one change here and everything's cool. All right? And this is actually really easy to test, right? I test this path, I test this path, I test this path. I'm good to go. I don't have to worry about that sort of grooved up, crazy code that's there. So spaghetti code is bad. Avoid creating spaghetti code. Flowcharts have their limits. It's interesting because the very first job I had out of college was with Boeing Aircraft Corporation, and they were making the F-18 fighter jets. Now this was a while ago, but it's interesting because the way they documented their assembly language code was using flowcharts. So they had flowcharts that told you how all the code worked. And they're beautiful flowcharts. Once again, this is back in the day, so we didn't have any really fancy PC tools to create flowcharts. So they had written their own sort of mainframe graphics program that allowed you to edit and create flowcharts. And it's interesting because when you got a piece of code that you were responsible for, what you really got was probably between 50 and 100 flowcharts that described what that code did. And then when you were assigned to actually make changes to the code, the very first thing you did was you figure out how you're going to update your flowcharts. And then after you got that done, then you actually went ahead and you made changes to the code itself. But I can tell you, flowcharts can very quickly become quite large, right? You won't be able to fit it on a single sheet of paper after a while. You could go to multiple sheets of paper, but then things get confusing. So look, if it gets too complicated, then what you do is you slide over and you start to crank out pseudocode, okay? And maybe, ultimately the documentation for whatever software you're writing is a combination of flowcharts and pseudocode. So whatever fits best. There is no magic silver bullet. There is no one correct answer. If you have a piece of software and you want to communicate to somebody else what it does, maybe it's a mix of pseudocode and flowcharts, depending on whatever gets you across the best. Verifying code. Test cases. We know about test cases. So how would you test this program? Remember, this is our federal tax program. Remember, it's got two decisions. Are you married or are you single? And then depending if you're married or single, the question is how much money you're making. If you're making a little bit of money, we're going to tax you at this rate. If you're making more money, we're going to tax you at this higher rate. Right? So there's really, I guess, 3 decisions. Married, single, and then how much money you're making. Okay? How would we actually test that? One possible way to test that program is run it with every single possible number. Okay? Do it for married, do it for single, and do it for somebody who makes $1, somebody who makes $2, somebody who makes $3, and go all the way up to whatever the largest number you can think of is. And if it works in all those cases, then you know, congratulations, your program is successful. But you nor I have time to do that, and that'd be sort of a silly thing to do. So our thinking is listen, if it computes 1 or 2 tax amounts in a given range correctly, let's just assume that it's going to do all of them. Okay? But here's the trick, and it's the magic word, coverage. We want to make sure that we have good coverage. So when we pick our test cases, we pick what values we're going to test our tax program with. We want to make sure that those are the values that are most likely to break. All right? So that's going to be the key thing there. We need to come up with a testing plan if we want to test our code. So we want to have a comprehensive set of test cases. Remember, there's 2 possibilities for marital status, so single and married. So obviously, we have to create tests that test single, test married. There's no question there. Then there's a handful of boundary conditions. Remember, I think on the single it's do you make more or less than 32,000, and I think on married it's more or less than 64,000. So those are magic numbers. So we want to probably test a little bit less and a little bit more, and maybe exactly that value to make sure the program makes the right decision. We also want to, of course, test invalid input, such as a negative income. How much did you make last year? In fact, you owe me more. That's fabulous. That's one. So those are the things that you want to test. So that's our testing plan. We're going to have plans. Okay, so you know, you can sort of map out what your testing plan is going to be. So here's our test case. We're going to have to say I'm 30 grand of input and I'm single. 72,000 and I'm single. 50 grand, I'm married. 104,000, I'm married. And then here's some of my boundary cases. Exactly 32,000 and I'm single, right? And then exactly at that point in time, it should shift over to one of the other. You know, by the way, I made nothing last year and I'm single. Let's see how it handles it. So this is, you know, you make a list of exactly what conditions you want to test, and then that's what you can actually base your test cases off. We go back to the flowchart here for a moment. If you have a flowchart that shows how your code works, it makes creating the test cases just that much easier. Because you can go to your flowchart, and as you test a given condition, you can obviously line out that particular one. And what you should see when you're all done, when you've created all the test cases that you need, you should have a sheet covered with X's. And you should be confident that you've covered every single path through your code. There was a test case that exists for that particular path. So if you design test cases before starting to code, you know about that. Working through the test cases gives you a better understanding of the algorithm that you're about to implement. Amen to that. Okay, Boolean variables. So we're going to shift gears a little bit. We're going to add to your knowledge of Python. So what kind of variables do we already have? We know about, let's see, integers, right? What else do we know about? We know about strings. What else? Floats. I mean, I guess we could throw in characters, but those are sort of small strings, right? Okay, cool. Great, guess what? Your list just went up to 4, because we just added Boolean, which is just cool to say, by the way. Okay, so sometimes you need to evaluate a logical condition in one part of the program and use it elsewhere. Logical condition. What's that? What is a logical condition? Yes or no? True or false? Yes or no? Okay. Is the light on or off? Do I have money in my banking account or not? That sort of stuff, right? To store a condition that can be, are you a zombie? True or false? Okay. To store a condition that can be true or false, you use a Boolean variable. So we have a very special variable that's designed to hold one of 2 values. One value is true, and the other value is? And what else can you store in a Boolean variable? Nothing. It can only take on 2 values, right? In Python, the bool data type has exactly 2 values, false and true. Notice that they start with a capital letter. A little f and a little t won't do it for you. These variables are not strings. They're not integers. They're special values just for Boolean variables. I had another student ask me the other day, so where do we set up true and false? Do we have to create a T system? And the answer is no, you don't. So please understand that in the Python language, as it stands today, it already knows what true is. It already knows what false is. Shh, want a secret? I thought false is 0, true is 1. But we're not going to worry about that, okay? We're going to keep that as a secret, okay? So it already knows the word true. It already knows the word false. So you can assign that to a variable anytime you want. Here's an example of Boolean variables in action. You ready? This is exciting. Failed equals true. That's it. Okay? Now, here we're going to use it in a conditional. If fails, then do something. That's sort of cool, because we don't have to do if failed equals true, or if failed equals false. We can just say if failed. And that produces the result that's needed to have the if statement get the value of it. So you can do some cool stuff. Or you can appear to be cooler than you are. Okay. When you make complex decisions, you often need to combine Boolean values. Oh god, it gets complicated. An operator that combines Boolean conditions is called a Boolean operator, and we've got 2 of these. So one is AND, yields true only when both conditions are true. And then there's OR, which yields true when at least one of the conditions is true. And and OR are your best buddies in the whole wide world. Anybody here electrical engineers? Working on electrical. So and OR gates. You'll do lots and lots and lots of stuff with this. Okay? Truth table. Let's make sure that you fully understand how and OR works. So here's one of our tables. It's sort of hard to tell. And here's another one of our tables. So let's take a look at our first table right here. So if A is equal to true and B is equal to true, then A and B is excellent. Okay? A is equal to true, B is equal to false, then A and B is, if A is equal to false and B is equal to true, then A and B is, and if A is false and B is false, excellent. So what you're going to find out here is that it's sort of hard to get A and B to be true, right? It only happens in one case, when they're both true. In all the other cases, the dang thing always turns out to be false. So it's a little bit of an effort to get an AND condition to be true. Okay, now let's go ahead and do OR. So if A is true and B is true, then A or B is, if A is true but B is false, then A or B is, if A is false but B is true, then A or B is, and if A is false and B is false, false. Okay. So now OR is a lot easier to work with, right? All I need is somebody to be true. OR says what the heck, oh, just change this, right? And our last little number here is not. A little operator called not, and it basically flips things. So if A is true, then not A is, and if A is false, then not A is. Sound fair? Not hard, not complicated. You just have to keep it straight in your brain. Okay. We'll do an example. Yay, we love examples. Okay, so you want to write a program that processes temperature values. Okay. Sort of like a thermometer, I guess. Okay. You want to test whether or not a given temperature corresponds to liquid water. What is it? Liquid, gas, solid. So, okay. At sea level, water freezes at 0 degrees Celsius and boils at 100 degrees. Okay, this is just keeping our math easy. Water is a liquid if the temperature is greater than 0 and less than 100. Alright, so here we got a little flow chart. Temperature greater than 0, true. Temperature less than 100, true. Then the water is a liquid. Okay, cool. Shall we take a look at what that is in Python? Why, certainly. If temp is greater than 0, here it comes, here it comes, here it comes, and temp is less than 100, then print liquid. Sort of seems like exactly what you would expect, right? So remember, both of these conditions have to be true, whatever that temperature is. Okay? They have to both be true, and then I'll print liquid. Okay? That was fun. Let's do more. Yay! Okay, so what is this? So if temperature is less than or equal to 0, which means that I've got ice, then I would say water is not liquid. If temperature is greater than or equal to 100, which means I've got gas, then I say water is not liquid. All right, so let's see what we got going here. If temperature is less than or equal to 0, here it comes, or temperature is greater than or equal to 100, then print not liquid. So I don't care about that. If this turns out to be true, I'm going to do this. If this turned out to be false, but that turned out to be true, then I'm going to go ahead and do that. Not rocket science, it's just a matter of getting it straight in your brain how this all works. Precedence. You guys remember precedence, your old friend from the midterm, right? Yeah, okay. So it turns out that Boolean operators are at the bottom. You work out everything else, and then you do your precedence for and and ors. Okay? Boolean operators and and ors have the lower precedence than everybody else. For that reason, you can write relational expressions on either side of the Boolean operators without using parentheses. So here you go. If you got temp is greater than 0 and temp is less than 100, you don't have to put any parentheses around these because whatever is there will get evaluated before the and is evaluated. So they're going to work out the whole shoot match there, and in order will do the very, very last thing they're going to work out. You can invert a condition, so this is pretty simple. If not frozen, print not frozen. That was just a Disney moment. Did you share it? Did you share it? Okay. I guess that's just alright. Boolean operator examples. 0 less than 200 and 200 less than 100 is, and why is it false? That is exactly correct. Okay. 0 less than 200 or 200 less than 100 is what? And why is that? But this is still false. So why did that turn it? Why is that? So that means what? All we need is 1, right? You got it, exactly. 0 is less than 200, or 100 is less than 200. Right? Now they're both true, so either one of them. Okay, cool. All right. Not 0 is less than 200. Well, is 0 less than 200? Because that would be true, right? Now we got this not thing there, so it turns a true into a what? Exactly. All right. Frozen goes true, frozen equals false. You don't have to do that. You can just say not frozen, and this one you can just say frozen. So you don't have to have that whole equals. Cool kids don't use equals with that whole. All right, your Python toolbox. Guess what? We've just added. I guess really and or not is what should fit in there. That's okay. Now you've got Boolean variables that you can use in your immense collection of Python tools. Pretty cool, huh? All right. What did we do today? We did flowcharts. Yay! We talked about creating testing plans. Always a good thing to do. We covered Boolean variables, and then we got even crazier because we covered Boolean operators, which are and, or, and not. Oh my gosh, your brain's completely full at this point in time. Is there anything left for us to cover? Why, yes. Next week, we start functions, a critical and key part of Python. All right, fantastic. We are good to go.